Hello. In this lecture we will talk about IKE Phase 1 main mode. In Phase 1, main mode is used. The first message that is going to be sent between the initiator firewall and the responder firewall is a list of proposed security association. This is nothing more than what encryption and what hashing algorithm it prefers to use, and what group keys for Diffie-Hellman it prefers to use. The responder would select one of those proposals and respond back to the initiator firewall. The initiator firewall will generate its Diffie-Hellman public key and send it to the responder. The responder would create the Diffie-Hellman public key and send it to the initiator. And now, both sides have the keying material to be able to create the shared secret key. And then once they have the shared secret keys, now they can exchange identities because they can encrypt the data and hash it. So nobody can see what identity and what are the information getting exchanged. The traffic will be verified and encrypted. And then the responder will do the same. And then Phase 1 is complete. One of the main issues with main mode is that it requires the IP addresses and shared keys to be known in advance. So, let's take a look at this in finer details. The initiator would send the first message to the responder firewall. That's message 1. The header of message 1 includes the security parameter index that's initialized, meaning it will put its own index here, a number that it picks. And then, the security parameter index for the responder is still zeros, because the responder hasn't responded yet. The security association, which is the transform set. Transform set is basically the part of the message containing what encryption, hashing algorithm the initiator prefers to use. It is a list, an ordered list for what the firewall is proposing to use for encryption and hashing. And then it's going to send other vendor IDs, which is other preferences that this firewall would like to use. We are going to talk about examples of vendor IDs in future lectures. The responder would now respond with the header, the security parameter index for the initiator, that's known already as it was sent in message 1. It's going to create a security parameter index for its side. The responder would generate an index number for its side of the connection. Based on the ordered list it received from the initiator, it is going to select one encryption algorithm, one hashing algorithm, and one group to use for Diffie-Hellman. And then, it will add the vendor IDs which provides the preferences information for its side of the connection. It will then send it back or respond to the initiator. In message 3, the initiator would create the Diffie-Hellman public key. Same like we discussed previously. Based on the Diffie-Hellman group, it will pick a random number for its private key. It will then generate the public key. It would send its identification, which is its IP address, and would send a number used once, referred to as nonce. So, this is the number from the initiator side. And that number will be used in calculating the shared secret materials, as well as the encryption keys, and the hashing keys. It is going to send this to the responder. The responder would now, because it knows the group that was selected, based on message 1 and message 2. It is able to do the next step, which is calculate its shared secret key, and now the responder has the Diffie-Hellman public key of the other side, which is of the initiator, and it has the group. It knows the Diffie-Hellman group to be used. Now it can create the shared secret key. And it's going to send its own Diffie-Hellman public key, and its own IP address identification, as well as the number used once from its side. And it is going to send it out to the initiator. The initiator will do the same, which is calculate the shared secret key. And based on this, they're both going to create something called the seed key. This seed key is used to arrive to additional keys. The seed key is going to be created by running a pseudo-random function, which is basically the hash function that was selected during negotiation. This includes the pre-shared keys, and the nonce used by the initiator, as well as the nonce used by the responder. So, the seed key was calculated using the same hashing function, which is the pseudo-random function. Now it's used for a different purpose. It's going to run a pseudo-random function, and for its input, it will put the pre-shared secret key, the nonce from the initiator, and the nonce from the responder. So, the pre-shared secret key is one part of this formula. And this can only be obtained if the two IP addresses are shared in advance, and the two sides are configured with the opposite side IP address and pre-shared key. So, that's why main mode requires that the IP addresses be known in advance. It's the way to look up the pre-shared secret. It is going to use that pseudo-random function. That's going to take the pre-shared key and the nonce of the initiator and responder. And then, it will produce something called the seed key. This key will be used to create additional keys. So there's a different name for the security parameter index of the initiator and responder, is cookie initiator and cookie responder. Those two terms are equivalent. Both sides will do the same operation. The first step is calculate the phase 2 key. And this is done by using the pseudo-random function. It will feed it the seed key, the shared secret, and the SPI from the initiator, as well as the SPI from the responder, and the value 0. This is called the phase 2 key, or SKID, D. The next step is to take the SKIDD, and then feed it into another pseudo-random function. This will take the key seed and then the SKIDD. It will take the shared secret key, the cookie from the initiator, the cookie from the responder, and then the value 1. This is the SKID, A. SKID A is used for authentication and hashing purposes. And then, it's going to calculate the encryption key. It will run the pseudo-random function again with the authentication key, SKIDA, the key that was produced from the previous operation. And it will use the key seed and shared secret key, the SPI from the initiator and the SPI from the responder, and then the value 2. And then it's going to create the encryption key. The encryption key is going to be used to create a hash. The initiator will calculate the hash as follows. It's gonna also use a pseudo-random function, feed it in the seed key, the Diffie-Hellman public key from the initiator, the Diffie-Hellman public key from the responder, the cookie of the initiator, the cookie of the responder, and the security association. And basically, what the security association is, it is the entire payload of the proposal message that was sent during the initial communication between the two firewalls. And then it's going to send this hash, along with the ID of the initiator, and it is going to encrypt the payload with SKIDE. So message 5 is encrypted. It includes the hash that was calculated, and it's going to send message 5 to the responder. So let's take a look at this in a packet capture. Just to understand what the initiator cookies, and all the terms we discussed. The first message, the initiator SPI. The first message, it doesn't have anything for the responder, because the responder hasn't responded yet. The security association is basically the payload of the proposal, which is proposed during initiation. And we see here, in this case, the proposal is just one proposal. So, this is transform 3 proposal. attribute encryption as AES, with key of 128, and the hashing algorithm proposed as SHA. The Diffie-Hellman key proposed as Group 1, which is 768 bits. That's what I am referring to as SA. So this message is used as part of the hash function. The payload, all the way to the end, is used as part of this hash function. So, that's from the initiator side. So the initiator side uses the Diffie-Hellman key from the initiator, and the Diffie-Hellman key from the responder, the cookie from the initiator and the cookie from the responder. This was not in the first message as there was no responder index. This is in the second message that has the initiator and responder indexes. So those two values are going to be used as part of the hashing function. And then, it's going to take that entire hash, and is going to add the hash to the payload and encrypt the entire payload with the ASCII IDE. ASCII IDE was calculated in the previous steps. And then it's going to send message 5 to the responder. Message 5 is encrypted. The responder will decrypt it and validate the hash. How is it going to validate the hash? It has the Diffie-Hellman initiator and Diffie-Hellman responder public keys. Those were communicated in message 3 and 4. It has the cookie initiator and cookie responder. It has the security association message. And it has the ID of the initiator. So, it has all the values that it needs to run the same operation and validate the hash. Then, the responder would run a hash for the responder. This would include the Diffie-Hellman responder public key first, and then the Diffie-Hellman public key of the initiator, the cookie of the responder, and cookie of the initiator. The SA message, the first message, and the ID of the responder. So, it's gonna add this hash with the ID of the responder and encrypt the payload with the ASCII IDE, and then send it to the initiator. That's message 6. And then, the initiator will decrypt and validate the hash. How is it going to validate the hash? It has the Diffie-Hellman key for the responder, and for the initiator. It has the cookie for the responder and the cookie for initiator, the security association, and it has the ID of the responder. It has all the values that it needs to validate the hash. This would complete phase 1. We will discuss more in the next lecture.